Hello and thank you so much for watching this fourth episode of the AI Red Team Academy. My name is Jarno Baselier and today we are going to pick up where we left in the last course. We learned all about neural networks and today we are going to take a look at one specific type of neural network, which is a transformer, where every token looks at every other token in the queue. It uses self-attention. Well, and all of the things I'm going to teach you today, why they are important, especially for large language models, etc. But before we do, I want to ask you to like this video. It is a YouTube video, so that's very important for the algorithm. And even more important is that you will subscribe to my channel if you think this is interesting. And if you want to follow all the other AI Red Team Academy courses as well, please subscribe to the channel. Very important to me. Thank you so much for doing so. And next, if you want to dive even deeper in all the topics, well, there will be a lot of you on YouTube, but you will not have all the slides, you will not have the scripts, you will not have special workshops, you will not have special videos. So there is a lot more content, and this content is only for my Patreon. So please consider becoming a patron because you will get a lot out of it and you will help me and the work that I do. Thank you for considering. Now that's all out of the way. Let's start with this fourth chapter. Let's take a look at transformers. Yes, welcome to the fourth chapter, the transformer architecture chapter, where hopefully more pieces of the puzzle will fall into place. We have a few things we need to discuss when we talk about transformers. We need to discuss which models were before transformers. We need to talk about tokens and text and embeddings. We have some position encoding, some self-attention mechanism, how this specifically works, and this is very important. We have transformer block structures, scaling laws, grouped query attention, which is a little bit of a sidestep, but it falls perfectly within this chapter. And know that just like many other functions in AI, that transformers are just transformers. There is even more beyond transformers. But since transformers is still something that is most of the time used, we will need to talk about this. So let's talk about this. At the end, well, you will understand how modern AI models actually work internally, including how they represent text, how attention lets models focus, and how transformers replace older architectures like RNNs. So we will work from tokens to embeddings to self-attention and finally through output. And this is important because without this, LLMs look like magic, but with this understanding, you can choose the right model for the tasks, tune prompts effectively, understand inference speed cost trade-offs, and grasp why transformers scaled at GPT-4, Llama, Cloud, etc. So this is important. Let's talk one slide about the old way, about RNNs and LSTMs. Before transformers, language models used recurrent neural networks or RNNs, where we have input being converted to words, which goes to the RNN network. We had some hidden state, or we had some hidden functions being executed, and then the next word was processed, etc. So this is in a nutshell, and this has a lot of limitations. For instance, processing, it's sequential, so it is pretty slow to train. The memory, it forgets long-range relationships, so it has just a little bit of memory or a short memory. Parallelization, it's impossible to across sequences. Scaling, well, it is very expensive, so this is not the best way, but this is how we did it before. RNNs learn from earlier context, but they struggle with long sentences. Example, remembering the subject at the beginning of a sequence of a sentence when forming the verb at the end of the sentence. The breakthrough came around 2017. Those were the transformers, because instead of reading text step by step and word by word, it lets every word take a look at every other word at once. And this specific thing is called self-attention. There were some immediate benefits by doing so. We had some parallel processing, which is much faster and thus much cheaper. There was better modeling of long-range meanings. It scales efficiently to billions of parameters, and this single architectural change is why models like GPT-4 even exist. This is what makes them possible, and this little Animation shows us in a nutshell what it is. We have some text that we put in, and that this specific text is being pre-processed, and by the encoder it's being encoded to vectors. Then it goes to some embeddings, and then the decoder decodes it back to something else. So maybe words are being converted to a different language, to numbers, etc. And finally it will give us a specific output. But this is in a nutshell what it does, but let's take a look at it step by step. And before we can even take a look at this, we discussed it a little bit before, but let's take a look at what a token is. A token is a piece of text that the model processes. The tokenizer defines how text becomes numbers. Neural networks are just giant math machines, so the input must be numbers, so everything must be converted to a number. And here we see some examples of tokenization. We have the word playing, which is being converted to two specific tokens, play and ing. The word your is being converted to two specific tokens, u and comma re. And then we have the Dutch Amsterdam, which is just one token. This is a common word, or multiple tokens. This simply depends on the tokenizer that processes the word, but usually, because this is a common one, it will be just one token. But this is how words are being converted to different tokens. So you can have a sentence with like 10 words. This does not automatically mean it takes 10 tokens. It can be 20 tokens, less or more. So why does this matter? Why do tokens and tokenization matter? It affects speed because fewer tokens is faster inference. It affects the cost because LLMs charge per token, and the less tokens you have, the less it costs. And it affects the meaning. Token boundaries shape the understanding. When an answer is too long, the model simply ran out of tokens in its allowed window. So another example of tokenization, you type hello, hoe gaat het? This is Dutch, but how are you? The tokenizer splits this into different words where hello is a token, the comma is a token, and the different words are tokens as well, and the question mark at the end is another token. Then there will be a vocabulary lookup, like 50,000 entries. So all of these tokens will be converted to numbers or IDs like you see here. And finally, all these numbers, which are in the step 4 in a numerical array, they become vectors by using embeddings, and each ID is converted to 512 numbers by embedding, so the transformer can do the specific math. This is important, so in the end your words become tokens, tokens become numbers, and numbers become vectors. Then talking about embeddings, what are they? Embeddings turn tokens into vectors or lists of numbers, and these vectors represent meaning and semantic similarity. Here we have some examples of the token king and of the token queen. Words relating to royalty, cluster, and unrelated words lie far apart. So you can see that king and queen are not that far apart by only looking at the numbers. When a number is converted to a vector, it becomes a list or an array of numbers. Usually 512 numbers. This means 512 floats, which is a point in a 512D or dimensional space, a dimensional vector. And here we see a short example of such a vector. And with this number, with these vectors, the transformers can do the math. Here we have a car, which is far away from king, so it will get a number that is far away from the number that king has. But queen and prince get numbers close to king because they relate to each other. And princess gets a number close to queen, which will also be pretty close to king, but a little bit farther away. And this is how the tokenizer and embeddings create a little bit of meaning. So what do the 512 numbers actually mean? The AI learns this during its training. Here we have different numbers from 1 to 500 or to 512 with one dimension. The possible meaning that is learned is formality, like hi. When we go a little bit deeper, there will be sentiment. More deep, is it a greeting, so it gets some context understanding, and at its deepest level, it can see how it is related to different things. So why 512 and not 1 or 1000? If you only had one dimensional, it would be too simple because it can't separate meanings, because meaning happens in the lower layers. If it is just 128 dimensional, this would be okay for small models, but it wouldn't fit large models or large reasoning and meaning. 512D seems to be the sweet spot. This is used in BERT, Roberta, etc. And more than 1024 dimensionals is especially for bigger models, Llama, Grok. But most of the time we work with 512 dimensional layers or dimensions. Here we have another Dutch example. Let's see if we can. All the follow-up slides will have English examples because, well, this is a course that I did in the Netherlands, and that's why these Dutch words are there. But even so, we have hello and good morning, two of those words. You can see that this is an array of 512 numbers. This is another array, but looking at the numbers, they are pretty close together. So it knows they mean the same thing. Here we have something different. We have the numerical value of 25, and here we have the words of 25 euro, but in Dutch. And here you can see as well that the numbers are pretty close together. So they have the same meaning, exact amounts correctly. So both of them will be first converted to tokens and then to vectors, where the vectors will be pretty close to each other. The bottom line here is that words are not magic. They become numbers, most of the time 512 numbers, and then the transformer does the normal math. And suddenly AI does understand Dutch or English or numbers, etc., and how they relate to each other. Transformers process all words at once, no left to right order. They must learn where each token is in the sequence. So without position info, the sentence "the cat sits on the mat" is the same as "mat de on sits cat the," because we have no positional information about the words. There are two common methods to add position. One is absolute position encoding with a sine or cosine patterns, and we have relative position encoding, which is distance based. And this lets the model understand the word order, the sentence structure, and the grammar patterns. Most of the time, for the two common methods right here, the relative position encoding or distance based is used most of the time. Looking at absolute position encoding, sine and cosine patterns, this is from an original 2017 paper. At the first position, 0, we have the token the, which gets a position or vector, a sine and a cosine. Then we have the second word, position 1 is the cat, which gets another one, and it goes from 0 to 1 to 2, etc. And each position has a unique 512D wave pattern. The model learns position 1 is the subject, position 2 is a verb. It has a fixed maximum length of 512 tokens, and this is used in BERT and early models. This is still being used in a lot of places, but this is the better way, the relative position encoding. And now we only care about the distance between words. So between cat and between sits, there is a distance of 1. So this holds some relation, and it gets an attention bias of 0.8. The cat and mat is far away from each other, which gets a distance of 4. There are 4 words in between. The cat sits on the mat, so mat is the 4th word after cat. And it gets a lower attention bias of 0.3. And here we have the same thing. The words on and the are next to each other, so it again has a distance of 1, and it gets an attention bias of 0.8 again. No fixed positions, and this works for 32k plus tokens, so with much larger token windows. It is faster and way more flexible. As an example, here we have again the cat sits on the mat. If you take a look at absolute, then each token gets a position number, 6 vectors or 6 words will get 6 positions, 0 to 5. And for each position, we compute a 512D vector using a sine and cosine. And with relative, we get attention, where the cat is strongly attends to sit, which has a distance of 1, and weakly to mat, which has a distance to 4. So it calculates the relative words to each other and usually gets a lot better results. So each word learns to focus attention on other words that matter. We have again another sentence as an example. The cat, which was black, sat on the mat. The attention connects cat and sat together. And this way the model learns relationships, not just proximity. The first step in this is input. And in this example, we might have 6 tokens, which become 6 vectors in a 512D each vector. The second step is that each token makes 3 versions. We have the query, the key, and the value, the Q, the K, and the V. The query, what am I looking for? Which might be cat. What do I offer? Well, what is the cat doing? It sits. And the value, what do I have? The value is what information do I have as of this moment, is that we know that the cat is sitting. So sits in this case is relevant. If this would be some other word like and, then we have cat and those are not relevant, and that would be the conclusion or the value, not relevant. So we give it a score in the third step, like cat and mat is low, because mat is far away from cat. So the final score will be a lower score. Then the fourth step will be soft max, where all of those numbers are being, the softback turns arbitrary similarity scores into positive values that sum to 1, so they can be used to compute a weighted average of the value or the V vectors. So 0.7 becomes 70% sits, this becomes 20%, and 1% for mat, because mat is the farthest away, and sits is pretty close to it, to cat. And then we have an output where cat is most likely related to sits, because that's what it's doing, not so likely on the word on, and even less likely is related to the word mat. So now cat knows it is sitting on the mat because sits has gotten the highest score. And here we see another self-attention diagram where the quick brown fox jumps, where each vector gets a Q and a key. And then we get some attention scores in the matrix where the scores are being calculated. And finally, it understands fox is modified by quick brown and performs the action of jump. And this outputs the weighted sum of all those words and how they relate to each other. And this in another schema, basically the same thing that we just told. That is self-attention, but self-attention is one smart part of the transformer block. And that's only if it is an encoder block, because we have encoder and decoder blocks. But a transformer block is like the Lego brick of AI. One block contains 4 smart pieces. And we can stack 32 to 69 blocks like ChatGPT, Grok, Llama all use those. A transformer block is the repeating unit in all modern language models. Think of it like a Lego brick. You can stack many identical bricks to build a tower. And BERT uses, or at least BERT basics use the 12 blocks. Llama 8 billion parameters uses 32 blocks, and 70 billion parameters uses 80 blocks. So the more parameters, the more blocks are probably being needed. Like I told you, there are encoder and decoder blocks, and they are part of their own tower. Multiple stacked encode and decode blocks. So let's see. The encoder tower understands input. This is the listener, and the decoder tower generates output, which is basically the speaker. So we find self-attention in the encoder block, and the masked version in the decoder block. We do not have cross attention in an encoder block, but we do have it in the decoder block. And both blocks, encoder and decoder, all have a feed forward layer and add and norm steps. And we can see those here as well. So let's take a closer look at the four smart parts of the encoder transformer block. We have the multi-head self-attention, the add and RMS norm, which was previously called layer norm a function. We have a feed forward network and again the add and layer norm function. So first we have the multi-head self-attention, which is basically who should I ask to, who should I talk to, and here each token decides which other tokens are relevant to it. So every token compares itself to all the other tokens using attention scores. Important tokens get more weight, unimportant tokens get less weight, and multiple attention heads do this in parallel, so each focusing on different types of relationships, for example, syntax, meaning, or positioning. Then the add and RMS norm step kicks in, which is don't forget yourself, and this is to preserve the original information while adding new context. So the output of the self-attention is added back to the original input, where we see output is x plus attention x. And this residual connection ensures the model doesn't lose what the token originally meant. RMS norm then rescales the values to keep activations numerically stable. Then it goes to the feed-forward network block, think deeply alone. This is where each token independently processes what it has learned. After gathering context, every token is passed through the same small neural network, two linear layers with a non-linear activation like GLU in between. No communication happens here and each token reasons on its own, but then more deeply. And finally, we have the add and layer norm layer again to stay stable. The function here is to prevent training from becoming unstable as depth increases. The FFN output is added back to its input, where output is x plus FNN of FFN x, where layer normalization then smooths the values, keeps gradients healthy and allowing many transformer layers to stack without breaking. That is what happens here. Here we have an example, self-attention, where we have cat that asks who is related to me, what is related to cat. It focuses for 70% on sits, for 20% on and for 10% on mat, just the scores we have seen before. And now cat knows it is doing something on something, it is sitting. And then we have the add and norm part, where original cat plus new information, so the updated cat, and RMS norm keeps the numbers in a safe range. In modern models, this step is performed before self-attention, and then we call this the pre-norm step. Then the feed-forward network work, where each token thinks alone with a, in this case, 2048 dimensional hidden layer, and GLU adds non-linearity that can learn complex IDs. And then the final add and norm part, where the original and the new thoughts is the same, or is the new final updated token. RMS norm keeps the numbers in a safe range. And then finally, at the end, the full sentence is understood. Why residual connections? Why add and norm? Because without residual, then gradients vanish after 10 layers. Deep output is layer 10, where layer 9 and all the layers are within this. And with residual, then gradients flow directly, where the output is the same as the input plus the things it is learned. And this allows for more than 100 layers without dying. And why RMS norm, or previously known as layer norm, is being used? Because it normalizes each token's vector, it prevents numbers from exploding or shrinking, and it makes training stable and fast. So the transformer block is to talk, the attention to think, FFN, remember residual, and to stabilize is the norm. Modern chat models only use the decoder blocks and no encoder blocks. So original transformer, in 2017 we have encoder and decoder stacks, and modern large language models like GPT, Cloud, Llama and Mistral have a decoder only stack. It was used for if it's used for translation, we still have an encoder and a decoder stack. But if it is just being used for LLMs and thus text generation, we only have the decoder stack. And when it needs cross attention, we can still use encoder and decoder. But when no cross attention is being required, the decoder only stack will suffice. So in chat models, we only need to generate. So the encoder tower is being removed, but the decoder block still does self-attention and feed forward at every layer. No encoder means no cross-attention. So in ChatGPT style models, the decoder blocks look like this. We have the masked self-attention, we have an add and norm layer, we have the feed forward layer, and again the add and norm layer. Just like we just seen. Let's take a look at some scaling laws and why bigger models work better, because bigger models have more parameters and those can learn more patterns, more concepts and more relationship, but it requires more compute and thus more memory and thus more money, having diminishing returns past certain scale. Let's talk a little bit about grouped query attention in transformers. Grouped query attention balances speed and quality in transformers models. Faster inference, it has a faster inference than multi-head attention MHA and a better accuracy than multi-query attention MQA. It splits multi-head attention into groups. Each group shares key value heads but uses unique query heads. This one is introduced in 2023, used in Llama 2, the meta one, and Mistral 7B. The core mechanism here is that the multi-head attention baseline, each of the number of heads computes separate Q, K, and V projection, which is high in compute and memory. MQA extreme, all heads share 1 KV head. This is very fast, but accuracy drops. And GQA of the grouped query attention like this. This is the middle ground, and this will divide the number of heads into groups, and each group share 1 KV head. For example, when N is 32 heads, G is 8 groups, then we have 8 KV heads in total, and this is 4 times fewer than MHA would use, so 4 times faster. So this is simply a better and faster technique. We have some speed benefits, as you can imagine, where inference is 2 to 4 times faster because of the KV cache access. There's a smaller cache. Memory cuts KV cache off by 30 to 75% using MHA. So a 70 billion parameter model that was 140 gigabytes in memory now is only 4 gigabytes in memory. The throughput is upped by 20 to 50% on tokens per second. And this is depending on which GPU, CPU, etc. is being used. There's a quality trade-off because near MHA accuracy has an accuracy of 0.1 to 0.5, which beats the MQA by 1 to 2% on benchmark like GlueA and SuperGlue. Here we have a quick compare. The number of heads, the speed, the accuracy, and the use case. GQA is mostly used in production LLMs. For some real-world examples and when to use, the models that use GQA are Llama 2, the 7B and 70B billion parameter models. This enables efficient long context serving. We have Mistral 7B, which tops open source leaderboards with super fast speed, and we have Palm 2, which is an early adapter for scaling to 540 billion parameters. So when it matters, when inference heavy apps use it, chatbots, APIs, etc., where we can reduce the latency from 200 milliseconds to only 50 milliseconds per token, so 4 times as fast. With edge deployment, which fits larger modules on limited VRAM, and for training, this has a minor use, but mainly post-training optimization is where this shines. So the key takeaway is that the GQA makes transformers faster and smarter by trading minimal accuracy for massive efficiency. Know that grouped query attention exists and that it is pretty fast, but there is more than just transformers. AI models learn and store data in various ways. Transformers lead today and the process sequences with attention. Other methods do exist. They handle tasks like prediction or generation. Examples include RNNs that we discussed and CNNs for time series. State space models like Mamba offer speed. Google's Titan brings long-term memory focus. So for transformers basics and limits, transformers use self-attention. They weigh input parts for output, and this helps in language tasks. They scale with data size, but they struggle with long inputs. Memory grows quadratic while they forget old data fast. For an example, Google Titans architecture. Google released Titans in 2025. It evolves from transformers. Titans add human-like memory. So the core idea for Titan is it to separate short and long-term memory. Short handles the current context while long stores key past data. How it works, Titans use Mera's system. It selects what to remember and it updates, their updates happen on novel info only. The process here is input goes to short memory, surprise detector flags new items, long memory updates selectively, and this keeps the efficiency pretty high. And this is, in short, what it does. The Titan advantages over transformers. Well, it handles 2 million tokens at once. It uses less compute for long tasks. It reuses memory across sessions. It outperforms in accuracy on benchmarks. It scales better for long-time learning, and it reduces forgetfulness in AI. So a lot of advantages. The key takeaways for, at least for transformers, is that tokens represent text in model-compatible form. Embeddings encode meaning numerically. Position encodings preserve sequence. Self-attention learns relationships between words, and transformers scale better than previous architectures. But there are modern architectures that might become the default in the future. And this marks the end of this pretty theoretical module. I hope that you liked this video, that you liked the things that we discussed and the things that we learned. And of course, I know that there were a lot of things in here that were maybe hard to grasp, and you don't need to know every nitty-bitty detail of it, but you need to know what transformers are and how they work and how data is being processed, that data is being converted to tokens and tokens to vectors. And well, we will talk about vector databases later on, but know that this is part of the transformer architecture. And there's a lot we can say about this, but I think we said already enough. So yeah, this was it for this specific video, and I hope that you liked the video a lot. And if you do, I hope that you will like my video on YouTube. That will help me a lot. And please subscribe to my channel if you haven't done so already. It's really important. And what I want to ask you as well is if you might consider becoming a Patreon, because Patreons get a lot of extras. Yes, almost the complete AI Red Team Academy course is for free on YouTube, but we will have some deep dive lessons. We will have some special workshops. We will have some special deep dive videos. We have scripts and we have slides, and all of these things, they will only be available to my Patreons. So for future lessons, maybe we will work with scripts, etc. And those scripts, well, you can see them, but they will be pretty small and it will be a lot of work to type them over. So become a Patreon and you can simply copy and paste the script yourself. That being said, I think that Patreons get a lot of extras, and above all, you will support all the work that I do and show your appreciation as well. So thank you so much for considering. But for now, again, I thank you so much for watching this, and I hope you have an amazing rest of the day. Enjoy, hope to see you next time, and bye bye.